Okay, so let's talk about the ultimate computing race. On one side, you have the fastest supercomputers on Earth. These massive machines that fill entire buildings and guzzle megawatts of power. And on the other side, a challenger with a totally different playbook, one that uses the bizarre rules of the quantum world.
But here's the thing. The real question isn't about being just a little bit faster or even a lot faster. It's about hitting a milestone so huge it gets its own special name: quantum computational advantage. This is that moment, that tipping point, where a quantum device solves a problem that is, for all practical purposes, impossible for any classical computer to solve, ever.
And this is the story of Jiuzhang 4.0. It's a photonic quantum processor that didn't just win this race. It basically lapped the competition so many times that the finish line isn't even in the same galaxy anymore. It achieved a speedup so mind-bogglingly huge, it completely rewrites the rules of what we thought was possible. To really get what an incredible feat this is, we first have to understand the battlefield. See, this isn't some all-purpose race. It's a competition that's laser-focused on solving one very specific and fiendishly difficult type of problem. That problem is called Gaussian Boson Sampling, or GBS. The easiest way to think about it is like a giant, unbelievably complex Plinko game. From The Price is Right, but instead of chips, you're using individual particles of light, photons. You drop them in, they cascade through this maze of pathways, and the whole challenge is to predict the exact final pattern they create at the bottom.
Now, for a regular computer, this is an absolute nightmare. With every single photon you add, with every new path in the maze, the number of possible outcomes just explodes, exponentially. It gets so big so fast that even the most powerful supercomputers on the planet just hit a wall and give up.
So, this is where our quantum challenger steps into the ring. A photonic quantum computer, a machine literally built to play this game of light-based Plinko. But, and this is a big but, it had what everyone thought was a critical and totally exploitable weakness.
And that weakness, it's called photon loss. It's just unavoidable. As these little particles of light zoom through the optical maze, some of them are just bound to leak out and disappear. For years, the big theory was that this leakiness was a fatal flaw, because losing photons actually makes the problem simpler, maybe even simple enough for a classical computer to fake or spoof the final result.
And this leads us to the absolutely brilliant counterattack from the classical computing side. Instead of trying to simulate the perfect quantum system, programmers developed a clever algorithm designed to exploit that exact weakness.
It's called the Matrix Product State Algorithm, or MPS. You can think of it as the ultimate cheat code for a classical computer. It was engineered from the ground up to take advantage of photon loss. The more photons the quantum machine lost, the easier and faster it became for the MPS algorithm to just fake the answer.
So, this set up the perfect showdown, right? On one side, you have a leaky quantum computer, and on the other, you have a classical algorithm specifically built to prey on that leakiness. The stage was absolutely set for a definitive face-off.
But then, a new player entered the arena and just completely flipped the table, and its name was Jiuzhang 4.0.
Just look at the sheer scale of this jump. Seriously. Previous experiments were detecting, 76 photons, then 113. Jiuzhang 4.0, it detected up to 3,050. That's not just a small step forward, it's a colossal leap. It's more than an order of magnitude bigger than anything that had ever come before it.
So how on earth did it do that? It used a revolutionary design called hybrid spatial temporal encoding. Now, in simple terms, they built a much bigger and more complex Plinko board by using both physical space and carefully timed pulses of light. This new design was so good it achieved an incredible 51% system efficiency. And what that means is the maze was now so vast and so good at holding onto its photons that the leakiness just wasn't enough of a shortcut for the classical algorithm anymore. At this new scale, that MPS cheat code, it just stopped working.
So, what does this massive leap in scale actually translate to in terms of raw speed? You might want to brace yourself for this because the numbers are, well, they're just astronomical.
Okay, so Jiuzhang 4.0 produced one valid data sample, one correct answer from that insanely complex game in just 25.6 microseconds. That is literally faster than you can blink.
Now for the other side, to do that exact same task, the world's fastest supercomputer, a beast called El Capitan, would need, get this, more than 1 trillion times the entire age of the known universe. Let that just sink in for a second. This isn't just about being faster. This is a totally different kind of speed. It crosses a fundamental line between something that's just really, really hard and something that is physically impossible for any classical computer we could ever dream of building. And that brings us to the final score. The total speedup factor is more than 10 to the 54th power. That's a 1 with 54 zeros behind it. It's a number so ridiculously large, our brains can't even properly visualize it.
But wait, how do we know the quantum computer wasn't just spitting out random garbage? Well, they proved it wasn't. They use a metric called a correlation score, where a perfect result is 0. Jiuzhang 4.0's score was unbelievably close to that perfect 0. Meanwhile, every classical attempt to fake the data, including that powerful MPS algorithm, failed, and failed spectacularly. Their scores weren't even in the same ballpark. Okay, so why does this one very specific experiment matter so much to the rest of us? Because this is way bigger than just winning a single race. It marks our arrival at a brand new frontier in computation.
What this experiment did was establish what scientists call a robust demonstration of quantum computational advantage. It proved, beyond a shadow of a doubt, that by scaling up the hardware and keeping the noise down, a photonic quantum computer can crush even the smartest classical algorithms designed to beat it. It reached a level of performance that is truly, fundamentally impossible to simulate.
And the implications of this are just huge. This is a critical stepping stone toward building fault-tolerant quantum computers. You know, the kinds of machines that could one day help us discover new medicines, invent revolutionary materials, or even create more powerful AI. It guarantees that this race between quantum and classical computing is only going to get more exciting from here. So, this definitive win doesn't end the competition. In a way, it signals the real beginning. It forces us to look past what we thought were the limits and start asking a really thrilling new question. What challenges, what problems that we once thought were forever beyond our reach are now, finally, within our grasp?